This is Audiommunity, a podcast about our body's never-ending fight with the outside world.
Hi everybody, and welcome to Audiommunity. This is episode 11. We're recording on Monday, March 9th, 2015. With me, as per usual, is Kevin Bonham.
Hello.
And Kate Frowns.
Hello.
And none of us are drinking. It's really sad.
Yeah.
I know, I was just thinking maybe I should just grab a beer out of the fridge.
You'd be the only one.
It's not a bad idea. I mean, I could potentially do that too. The fridge.
Oh yeah, Matt, you're at home.
The fridge is yeah. So I think we're a week off in posting this, and I think it's worth mentioning the saga that was trying to record this episode, which included.
I mentioned it briefly in my last mini-sode, but
okay.
yes.
Well,
anyway, please tell us from your perspective.
No, I mean I haven't had the internet, right? So I bought a house in Atlanta. And it took me a little while to decide that I needed some form of entertainment, or at least to be connected to the world. And so I've been, doing these podcasts from work at Emory. And so we had a couple different trials in order to get this episode up off the ground. But anyway, my computer died in the meantime, and I was at work for a long time, and yeah. So now I'm at home because I decided to join the 21st century and get the internet.
Well done.
Yay! Now you can watch a Bachelor finale. Is that why you get the internet?
That's definitely why Matt would get the internet.
Yes. Also, I learned that Google Fiber is coming to Atlanta.
I hate you so much.
Yes.
You lucky bastard.
Kevin is so jealous.
I'm going to give them all my money. I'm going to give them all of it. Yep. AT&T, the guy was nice though. I will give AT&T the fact that they only backed out of our initial agreement one time. Okay. But our opening relationship move was for them to call me a day later and cancel the appointment that they had made.
Cool.
So I was like, this is a great start. But the guy was nice. Yeah. So today we're going to be talking about something that's a bit of a departure actually from some of the things that we've been talking about before. And it's something that I think is very seldom studied within the immunological field, and that is the immunology of pregnancy. And so I guess before studying immunology, before going through grad school, I didn't really understand that those two things had anything to do with each other. But it turns out that they are actually really heavily intertwined for a couple different reasons. First of all, because as Kevin has pointed out in the past, growing fetus on multiple occasions, including one of the attempts at recording this episode previously.
Right, yes.
A growing human fetus is essentially a giant parasite.
From the perspective of the mother's immune system.
Correct. Mm-hmm. So what you have... I mean,
also in reality, but we'll just let that slide.
Yeah, well, we don't have to go into that. So, yeah, but if you think about it, half of the growing fetus's genetic material, including half of the MHC molecules, and that is something that we've talked about before. We've talked about how bad it is to have a transplant where the MHC molecules don't match the recipient. And so essentially you have this growing organism that doesn't really look like self anymore. Maybe half of it looks like self, but the other half looks like dad's self. And mom has no way of knowing what dad's self immune system looks like. So you have to have some sort of mechanism for the mother not to just essentially reject the fetus out of hand saying, well, this is foreign. And that's something that I think this paper that we are going to talk about today brings up. While I'm on that topic, I should probably say the title of it. It is Seminol CD38 is a pivotal regulator for feto-maternal tolerance. And this is a paper, the first author is Byung-Ju Kim, and the last author...
interject real quick and say, that's not seminal as in, this is the seminal work describing this. We're talking about stuff that's in semen. Correct. It's also not the Florida Native American tribe.
Right. Seminole. Yeah, it's not a Seminole. It's Seminole. Also, I think we should apologize at the beginning of this. I'm sure that this is not going to go without some giggling. So hopefully PhDs in immunology can get through work dealing with seminal fluid without just going nuts. So
yeah, but only you and I have PhDs.
That is true.
Lacking, so
That's
maybe
very
she's
true.
going to be
and it's in virology,
inappropriate.
which is the superior science. So I will have no problem getting through this. Anyone who knows me knows that is a dirty lie, but whatever. I'll give it my best shot.
We'll find out. Yeah. So, I mentioned the first author, Byung-Ju Kim, the last author, Oh-Hyun Kim. So I apologize, as always, if I butchered those names. But they are out of the National Creative Research Laboratory in Jeonju, Korea, actually. So
that is an awesome name for a place, Creative Research Laboratory.
Yeah,
I want to work there.
National
Sounds
Creative
like
Research Laboratory. Actually, I cut it off even. It's the National Creative Research Laboratory for Calcium Signaling Network and Departments of Biochemistry, Urology, Pathology. And that is at Chobuk National University.
That's quite a mouthful.
There's a lot going on there. So like I said, one of the reasons that pregnancy and immunology are so interesting is because this idea of tolerance, and that's something that we will certainly talk about. But it turns out that there are also lots of other links that pregnancy has to immunology. One is an unexpected and very strange link to autoimmunity. And so if you're talking about tolerance, obviously one of the major issues with breaking tolerance in human disease is this emergence of autoimmunity in various different forms. But one of the things that really stands out about pregnancy is that for some reason or another, pregnancy and the modification of tolerance surrounding pregnancy has a direct impact often on someone's symptoms if they are suffering from autoimmune diseases. So one of the really strange things that we were taught going through grad school was that patients with MS, women with MS, for some reason or another, seem to have fewer symptoms when they get pregnant. Something about the pregnancy itself seems to tamp down symptoms in MS. And so it seems like, if you want your autoimmune disease to go away, get pregnant. And that is true for some diseases. RA, I think, also has a beneficial effect of pregnancy, but it's definitely not true across the board. So lupus, for example, and we've talked a little bit about lupus, but lupus is essentially an immune response against DNA within your own body. You produce antibodies. Basically, you get this huge systemic autoimmune response. It's really nasty. And so in the case of lupus, getting pregnant can either be neutral or it can exacerbate disease. There's a really nice review on the effect of pregnancy on autoimmune disease out there. We'll make sure to link it at the episode. It's actually really fascinating stuff, and there's very, very little as far as primary literature on this sort of thing. So I think those are the two main things that people will think about when they're talking about pregnancy and immunity, and it all centers around this tolerance idea.
I just want to interject real quick and say that for a long time, the thought about, so let me back up for a sec, the contradiction of pregnancy from the point of view of the immune response, what I say is the fetus being a parasite, that's been recognized for a really long time. And the explanation for quite some time was that the uterus might just be an immune privileged zone. In other words, there were some mechanisms by which the immune system of the mother was sort of excluded from ever encountering the fetus. So if it's sort of walled off and separate from the mother, then maybe the immune system just could never see the fetus. But it turns out that there's a huge amount of really direct contact between the immune cells of the mother and of the fetus. There's essentially their circulatory systems, their blood is almost completely commingled at the placenta. So you have blood vessels that are directly in contact with each other. You have immune cells constantly taking up antigen that is from the fetus. And so this idea that the fetus is somehow immune privileged or separated from the mother's immune system is incorrect.
Yeah,
and so that's part of the impetus to try to find other mechanisms that it might be protected.
Right. And building on that idea, actually, one of the things that the review brings up is that people have now found something called microchimerism. So we've talked about chimerism before. It's basically when you take an immune system from one animal and put it into another, right? So you're creating a chimeric mouse, usually, right? Where you've ablated one and you've put in the other. It turns out that humans experience microchimerism, and you can find mom's cells in the offspring well after birth into their 20s and 30s. So anybody listening to this, you probably have mom's cells still around. And actually, it seems to be true of offspring to mom too. So you can find offspring's immune cells in the mother well after birth. So it seems like you create this really interesting systemic chimera, and who knows how that influences overall tolerance to the growing fetus, which I think could be really interesting.
Right. Hard to study, though.
Oh, super hard to study. And also, I don't know that pregnancy immunology is getting a ton of funding currently.
That is probably true.
Which,
One reason, actually, so there was a graduate student a few years ahead of Matt and I in the immunology program that was trying to study some stuff about macrophages during pregnancy. And she always talked about how hard it was to do the research, not just because of funding. She was in a lab that had plenty of funding, but it turns out that our favorite research animal, the mouse, has a very, very different system of pregnancy than humans do. So we're both placental mammals, so there is a lot in common. But the structure of a mouse uterus, the way that it gets pregnant, they're basically in estrus every 3 days. So they can get pregnant really often. They can also have...
That sounds awful.
They also sometimes eat the heads off of their babies. So
no, they usually leave only the heads.
No. The heads are nutrition rich. Yeah.
I have found heads in cages. Yeah, where they ate everything. But that's neither here nor there.
Yeah.
The point is, they can also have, the other thing I wanted to mention is that they usually have more than one offspring, sometimes up to 8 or 9 pups in a single litter. So structurally and biologically, there's a lot that's different between a mouse and a human pregnancy. What that means is that studying human pregnancy using a mouse model is somewhat complicated. And this is important for this study in particular because it is using a mouse model. So we basically have to take everything in it with a bit of a grain of salt.
Right. So before we jump into the paper, I wanted to mention this other interesting aspect of immunity as well that we've touched on before that I think is probably involved here, and that is the idea of barrier immunity, right? So we've talked about how complex the physical barrier of the gut is in relation to the immune system and the vast effect that barrier and the interaction essentially between your host immune system and the microbiota in the gut, right? We've talked about how changing that environment can even lead to alleviation of things like MS, which I think is actually a super interesting connection here.
I bring that up every single time I have the opportunity.
Yeah.
We we're talking about it.
Yeah.
Yeah, it's I think that there's a lot to know here. I think that barriers generally is sort of an up-and-coming hot topic in immunology because it turns out that the vast majority of your immune system is actually at barrier sites. And I can't imagine that the placental barriers, things like that, aren't vastly more complicated than we currently give them credit for. I imagine there's a lot going on there, and somebody should do some really cool work on that.
Agreed.
So with that, maybe we should turn to this paper, which was published in PNAS, and it is a 2015? Yeah, February 3rd, 2015.
Yeah, I found this paper browsing Reddit, as I often do in the subreddit Science.
Instead of actually doing work?
I was looking at the subreddit Science, Kate. I think that I can justify that as being part of my research.
That's fine.
Yeah. So
we picked up on it pretty quickly.
Yes.
Even though it's taken us almost a full month to record this episode.
Right. Yeah. It would have been even more cutting edge if you can imagine that.
Yeah.
Yeah, because there's nothing that Audiommunity is if not cutting edge and always timely.
Yeah,
yes.
We're prompt. So this paper is essentially about looking at tolerance mechanisms in pregnancy, as Kevin mentioned before. And so, Kevin, do you want to start walking us through a little bit?
Sure. So one of the ways that allowed me to sort of get into this paper conceptually is the idea that we're not just talking about, when we're talking about the evolution of pregnancy, we're not only talking about the mother's desire to not reject the fetus. We're also talking about the father's desire to have his particular offspring accepted by the maternal immune system, right? So it's one thing to say that a mother doesn't want to reject her fetus because then she's never going to have any offspring. But there's also a selective pressure for fathers to have some way of influencing the rejection of their offspring. And so the place that these authors chose to look is in the semen of the male mice to see if there was any sort of immune modulatory component of male mouse semen that could have some effect on pregnancy of the female mice.
I have one small correction to that.
Mm-hmm.
As you read in the paper, there is a technical difficulty in obtaining mouse semen. Right. So it's actually the uterine lavage fluid and the seminal vesicle fluid, which I had to Google at work today. And was actually a little bit surprised when a penis popped up on my computer.
Mm-hmm. Safe search was off, apparently?
I mean, I guess I am in a hospital. Like, penises exist in hospitals as well. It's not necessarily a bad thing. But I was like, oh, I was not expecting that. I don't know what I was expecting. Googling things about semen wasn't that interesting. Moving on with my day.
Okay, so just to clarify, so the vaginal lavage is basically, if I remember correctly...
uterine lavage.
Oh, uterine lavage, excuse me. If I remember correctly, they waited to see when they saw a plug in a female mouse, which is basically, this is one of the particulars of mouse sexuality, is that after a male inseminates a female, there's a plug that forms in the vagina of the female mouse. And I forget if that's a function of the male sperm. It might be part of sort of male sperm competition. Or I can't remember if that's a response of the male sperm or if it's part of the female's biology.
I would assume it's part of the female's biology.
Really? In other animals this happens. It's definitely the male sperm trying to eliminate competition.
Yeah, I think it might actually be.
Really?
Mm-hmm.
Yeah, it's the males sort of plugging it up so that no other males can come in and compete for the affections of the female. But in any case, so the investigators basically waited until they saw one of these plugs formed, and then they did a lavage of the uterus. So they basically injected what I assume is PBS, phosphate buffer-saline, in order to wash out the contents of the uterus to find the male semen, basically.
I also learned about, what were they called? They were vesicles. So there are two parts, apparently, to semen outside of the sperm. There is...
Right, so the sperm is the reproductive cells.
Right, and then there's just sort of the fluid that everything is hanging out in, right?
Mm-hmm. That's the seminal fluid.
Right. And then there is this other component, which are these vesicles essentially released by the prostate. So there's sort of these packets of things. And so
a vesicle is just like a membrane-bound container.
Yeah, exactly. Yeah, I was actually surprised to learn that there's more in seminal fluid than just sperm and the fluid itself. It seems like other information is being portrayed in that interaction or conveyed in that interaction.
But we should clarify in this paper that a seminal vesicle is not actually a vesicle. That's a gland behind the prostate and the bladder.
Right.
Because so I was confused by that. I was like, what's the difference between a seminal vesicle and a what? So what you were talking about, the things that are actually like small membrane-bound vesicles. I'm going to mess up pronouncing this, but
prostosome. I believe.
Prostosome. Yeah. So what's the difference between the seminal vesicle and the prostosome? And so the vesicle is actually a gland the seminal vesicle is a gland that releases the seminal fluid, and then the prostosome. They are released by the prostate, and they all go out the same way.
All right. So the vesicle in this case, even though a vesicle is a membrane-bound compartment in cell biology, the seminal vesicle is an organ. It's like, I think it's a tube, right? Or is it actually part of the gland?
It's a series of tubes.
Yeah, okay. It's sort of like the internet.
Awesome. I think we've made that joke on this podcast before.
It's so funny.
All the time.
It's just so funny.
It's not, but it's just easy.
Okay, so it's strange that in this podcast, the thing we're laughing about is the internet and Al Gore, rather than talking about semen.
I feel like we're getting some in both.
Yeah, that's true. Okay, so this paper just starts out with CD38, which was a little bit confusing to me, but apparently this lab has been studying CD38. This is a protein that is normally found on the cell surface. It's a membrane-bound protein under normal circumstances, but they've found that there is, or no, I guess they hadn't previously shown soluble CD38. Is that right?
Right. Yeah. So it was known, I think, that CD38 existed in prostosomes.
Right.
But that is in a membrane-bound version of CD38.
Right. And they also knew that CD38 participated in some types of cell signaling that, depending on the context, can be associated with immune function. So calcium signaling is used in a lot of different cells, but it's also used in immune cells. And so they wanted to investigate whether the CD38 that was found in these prostosomes or found associated with seminal fluid might have some role in the immune system. And so the first thing that they did is basically look for CD38 in human and mouse seminal fluid. And what they found was sort of interesting. They found not only the normal membrane-bound form of CD38, but they also found a soluble form where basically the portion that is normally bound to the membrane is truncated. It's cut off. And what that means is that this protein, rather than being bound to a membrane, can just be floating around in solution.
And it did not sound like they had a problem collecting human semen for this study.
Right.
Healthy volunteers.
Yeah, it is much less complicated to acquire human semen than mouse semen, it appears.
Yes.
Okay, so the next thing that they did, I don't remember. It's been ages since I looked at this paper.
I know. I accidentally threw away all my notes on this paper, too.
But they basically looked and found the soluble CD8 through a couple of different techniques in semen, in both mouse and human.
All of those techniques you should be particularly familiar with because it's biochemistry. And
yes,
while biochemistry is the worst,
What?
You've done it pretty well in the past.
Matt has a particular animosity towards biochemistry because, as I think we have noted previously on this podcast, he tried to burn down our transfer apparatus.
Oh, that's right. That's right.
Hate.
And has not done a Western blot since.
And then Kate broke it.
No, I have not. Actually, that was, my rotation through the Kagan lab was the last time that I've done a Western blot.
That is somewhat depressing.
That blows my mind.
So great. Oh my God, it's so great.
No, I love biochemistry. That's all I do all day.
Yeah, because biochemistry is the best. All right, moving on.
Because it's a real science.
So once they found the CD38, they wanted to see, does this have some role in pregnancy, broadly speaking? And so naturally what they did, being good immunologists, or I don't know if they're immunologists, but being good scientists, is they found or created a CD38 knockout mouse. So they deleted the gene for CD38, and then they took male mice that didn't have CD38, and they mated them with wild-type female mice. So the idea here is these male mice can't get soluble CD38 into their seminal fluid because they don't have the gene for it. And they wanted to see, are these mice able to impregnate females? And what they found is that to a significant extent, far greater than in the wild type, males that didn't have CD38, their offspring or their attempts at impregnating females were unsuccessful a number of times because the females were reabsorbing the fertilized egg. So it wasn't that they couldn't get fertilization in the females, it's that there was something that happened probably to kill those developing embryos, so then the female mouse uterus reabsorbed them.
So I was really glad that they tackled that question, right? Because that's a super obvious question. Is soluble CD38 somehow involved in sperm actually reaching eggs to fertilize? And the answer is clearly no. You're getting lots of fertilization. You're getting normal implantation in the uterus. You can see where the eggs have implanted, but it's just very clear that the eggs from the CD38 knockout males, they don't survive. They don't thrive.
Right, and in fact, they looked directly at whether, if the total number of implantations, so in other words, after the egg is fertilized, it then has to implant itself on the uterine wall where it can start to develop the placenta. And what they found is that in these CD38 knockout males, their offspring were implanting just fine, but the number of viable implantations went down significantly. Yeah. And again, the rate of absorption went up of those embryos.
Along these lines, they also took a look at some really poor dendritic cell biology, just to show that...
Matt is a dendritic cell elitist?
I am. No, it's fine. It's fine. The way these fields sort of grow up is each individual field has its way of gating DCs, and it calls dendritic cell subsets something slightly different depending on what you're actually talking about. So the pregnancy field has established a quote unquote tolerogenic DC, which really doesn't mean anything, but phenotypically they show that these DCs do seem to lack the ability to form, I guess, this tolerogenic phenotype.
Yeah, so I'd never seen a TDC before.
Yeah, that's because it's not real.
Okay, so it could just be any DC that gets stimulated in such a way that it's going to release particular cytokines.
I mean, I'm sure that
Treg.
Yeah, I'm sure that there is a particular subset or subsets that are doing this. But a TDC is not a subset of DCs. It's an activation state of, yeah, exactly.
All right. Well, those criticisms aside.
Yeah, it's fine, by the way. The data are fine. Like, they show that DCs are not active in a way that would stimulate a tolerogenic response rather than a pro-inflammatory response. Yeah. So it's
and
fine.
they do also see a reduction, small, but a reduction in the number of T regulatory cells. These are cells that suppress immune responses.
I was not impressed.
Yeah, it's not big, but it's significant. I mean, they did statistics. They have quite a few.
Yeah, if you do enough experiments, your statistics become significant.
Yeah.
Yeah.
Also, it would have been good to know how well those T cells work, right? They show you that there's a difference in the number, but really they should be looking at how functional are those T cells. But again, it's okay.
But would you expect a biological difference between 14% and 11%? 14.2 and 11.7? I don't know.
I mean, you definitely could. I mean,
it's possible, but that's why I think it's more important to know what the functionality is, right?
Yeah,
if you find that those 11% are still perfectly capable of suppressing, then what are we talking about? Yeah.
Right. Or it could be that small difference in number is really masking a profound defect in their suppressive ability, right?
Mm-hmm. Yeah.
You could have 14% of T cells, of CD4 positive T cells that are Tregs, and that 14% are all super actively repressing versus 11%, but none of them are repressing well.
Sure. Or there could be more T cells total because they don't give us absolute numbers. And the reason that it looks like it's reduced is because you have a massive influx of Th17 cells, for example.
Right.
But again, maybe that's not the way that it is.
Matt loved this paper.
No, I actually do. I actually like this paper a lot. I just think that the cellular immunology it's one of those things where I think they know pregnancy really well, and so they know enough of the immunology surrounding pregnancy that all of the data are valid. It's just not necessarily true that the data are presented in a way that the rest of the field of immunology would be like, oh yeah, no, that's, I know exactly what that means. So
right, this is clearly not immunologists writing this paper.
No,
but that's not a knock. That's not necessarily a knock against it.
Biochemists either.
I don't know. Some of their Western blots are pretty.
I mean,
Some of them are not.
Yeah.
But
I wouldn't really consider that to be the sign of a biochemist is a good Western blot, but maybe.
I mean, it's not, the blot they show isn't on fire, so they're better at Western blots.
So they're better biochemists than Matt is.
So there's that.
Yeah.
All right. Moving on. So we have this molecule, CD38, that there is a soluble form of, and it seems that without this CD38, with the knockout, they can't distinguish between the soluble and the membrane-bound form. But it seems like the presence of CD38 is necessary to get sort of normal pregnancy. If you don't have it, you get a decrease in viable embryos from each mating. So, and maybe Tregs, maybe dendritic cells are involved. So the next thing they want to do is look more specifically at these tolerogenic DCs. And perhaps, Matt, since you have a better grasp on the gating strategies for this stuff, maybe you want to go through figure 3?
Well, I mean, they're looking at classical activation markers, right? So CD11C is how you're going to primarily gate these things. They show that there's not a huge difference in CD11C. You wouldn't expect there to be. CD11C is not really inducible.
But it tells you that there's a similar number of these cells.
Yeah, sure. I think they're making most often arguments about MFI here. They're not so much talking about percentages, but
Right.
It's fine. Yeah. So they've got CD11C positive cells, certainly, in both the control and the mice that lack the soluble CD38. So that's fine. CD40, basically what they're showing is that CD40 increases slightly. The MFI actually increases on those DCs in the control versus the CD38. Is that a soluble CD38 knockout?
No, so they're using mice. They're using bone marrow derived dendritic cells.
Right.
They're using bone marrow derived dendritic cells, and then they're either treating them or not treating them with soluble CD38. So this is in vitro. This is in a dish.
Yep.
And then they're activating them with LPS.
Okay, right. Thank goodness. Right. I was so lost. I was like, aren't we talking about the LPS guys?
Yeah, okay. Sorry about that. No, I was lost in the experiments here. So
they're basically looking at the ability to induce activation of dendritic cells in a tissue culture dish in the presence of soluble CD38.
Right. And so BMDCs are classically inflammatory in nature, right? They tend to be triggered pretty easily by things like LPS. And when you trigger them with LPS, you get things like MHC2 upregulation, right? So you increase your ability to present to CD4 T cells. You increase things like CD80, CD86, which is B7-1, B7-2 for your historical immunologists out there. And that's going to provide the second signal. We've talked about that before, basically licensing T cells to start responding. So that's a classical activation marker. And then CD40, which is, again, just going to help interact with both T cells and also B cells in stimulating an immune response. So basically what they see is if you take BMDCs, you treat them with LPS, all of these classical activation markers go up. But if you take those DCs and you incubate them with soluble CD38 and then treat with LPS, a lot of those inducible activating factors do not come up to the same extent.
Yeah.
Right. And the next thing they do, I think, is pretty critical, because one could argue that you might see, I mean, even though they show the same level of CD11C, you might argue, well, maybe the cells are just shut off entirely in the presence of CD38, which would be interesting in and of itself, but they don't just show things going down, they also show things going up. So they show an increase in anti-inflammatory cytokines like IL-10 and TGF-beta, which to me is sort of the most impressive part of this, is that not only do you get less of the inflammatory markers, you actually get more of the anti-inflammatory signals that DCs can produce. So it's not just a sort of global downregulation of things, it's actually a skewing of the response.
So what does IL-10 at steady state production of BMDCs look like?
It's very low.
Is it?
I mean, essentially zero.
Okay.
Of bone marrow derived dendritic cells.
Yeah.
In tissue culture, you wouldn't see any
essentially
IL-10
zero
at steady state. Yeah.
Because an alternative explanation is you've got some level of IL-10 being produced, and then you hit a normal BMDC with LPS, and that actually drops. The production of IL-10 drops. But if there's no production at steady state, then...
But yeah, that's interesting, because they don't actually show the uninduced, the non-LPS treated DCs.
I would like to see that.
But
I'm sure that it's true.
Because you could, I guess you're proposing that there's an alternative interpretation if you saw that data, that if they naturally are producing a high level, and then you hit them with the LPS, they go down. So in B, when you see this increase in IL-10, this might be like no change.
Right. It would actually be indicative of shutdown. Yeah, like you just said, they're trying to show that the DCs aren't shutting down, and that would indicate that they actually are. But if the expression is zero, then that's not a problem.
Well, another possibility is that soluble CD38 by itself is inducing IL-10 and TGF-beta, and then adding the LPS is not doing much. So, or it's induced. Maybe the LPS is inducing the same amount, but you have a baseline level when they're in the presence of CD38.
Yeah.
Right.
One thing I was wondering was in the text they talk about they treated their soluble CD38 with proteinase K, which is it's just going to degrade all of your proteins, and they don't see any effect. They don't see the generation of the tolerogenic DCs. But I was more curious to know if the catalytic activity of the CD38 was important. Because spoiler alert, at the end of the paper, they don't actually know exactly what's going on, what the signaling...
CD38 have Is it an enzyme?
Yeah.
Or did you mean binding site?
No, it's an enzyme.
Oh, really? I did not pay attention to
that
at
it's
all.
an ADP ribosyl cyclase, ADPRC, which I am assuming is why they study this molecule to begin with, because they're in the Creative Research Laboratory for calcium signaling.
Mm-hmm.
Right.
So they say in here that there's some sort of, that CD38 assist in calcium signaling by making these second messengers. So, but they never really address whether or not the cyclase activity of the molecule is important. But if you chop it up into tiny pieces, it doesn't work anymore.
That is definitely...
So that's actually where
totally
my biochemistry jab came from, was like...
Got it. Boom!
Really? Were you not expecting that? Okay, I guess. I mean, I guess it doesn't act as a peptide. It's not acting by being degraded.
And we added random peptides to our DCs and did not.
Yeah, well, I guess,
on some level, I guess I could see that being...
There could be other small molecules in semen that are having this effect.
Or it could be like a peptide or something, I don't know.
Yeah, so getting rid of the protein is a good way of eliminating that possibility, that there's some small molecule in the semen that's doing this.
I would give it to a rotation student to do.
Right.
Maybe it was. It's a long list of authors.
Okay, so they also see in this case, again, so not only the activation markers, an increase in anti-inflammatory cytokines, and they also see a decrease in pro-inflammatory cytokines, TNF and IL-12, and they see increases in STAT activation. So this is a transcription factor that is associated with anti-inflammatory signaling, essentially. Is STAT3 involved in antiviral signaling,
No.
Kate?
No.
No, okay. I think maybe that's downstream of TGF-beta, although I don't remember.
Downstream of TGF-beta is SMADs.
Okay. I don't know what STAT3 is downstream of. It probably says it in the text, but I don't remember.
It's probably one of those homeostatic ones. Let's see here. It's not... I should have Googled this.
Well, while Kate looks for that, I'm just going to finish off this figure. So, then they do a sort of old school immunology technique that I haven't seen in modern papers in a really long time, and that's an MLR, or a mixed leukocyte reaction.
Yeah.
So basically, this is mixing together antigen-presenting cells and T cells in vitro, and for some reason that I don't fully understand, you get activation in a sort of non-specific way in an MLR. And what they see in their MLRs is that in the presence of soluble CD38, more of your cells become T regulatory cells. More of your cells become Tregs, essentially.
So I guess that's getting close to starting to look at functionality, I guess. The problem is that all of it is, like, an MLR is not spectacularly specific. BMDCs
or at all
are vaguely reminiscent of dendritic cells in vivo. Kevin, you are like black. It's just like your face on a black background. It's like having a conversation with a Sith Lord. I'm
going to take a picture just for posterity.
Thanks. Okay, so I Googled a little bit about STAT3, and STAT3 theoretically can be phosphorylated in response to interferon, but it also is phosphorylated in response to IL-6 and IL-10. So maybe it means nothing in terms of, since their earlier figure says that IL-10 is being induced, this might just be the IL-10 signaling.
Right, but IL-6 is a pro-inflammatory cytokine, so it could also be, I mean, it's not necessarily indicative. Okay.
It could be all the things.
It could be all the things, yeah. It actually could be all the things. But I would guess that it might be IL-10 signaling, since there is an increase in that and not in IL-6, and you don't see the phospho-STAT3 in response to the more inflammatory signaling. Wait, unless control is, by control they mean like the control DCs, not just like unstimulated, right? Yeah. So it likely is a response to the IL-10 and not to the inflammatory cytokines.
Right. They didn't look at IL-6. They looked at IL-12 and not TNF, but that's a minor point. Basically, you have a generally anti-inflammatory response, as far as we can tell. Okay, so figure 4 is a bit of a throwaway figure. Basically, so Kate mentioned the enzymatic reaction, and I guess I totally glossed over it, but figure 4 is basically saying that CD38 has two roles, one of which is the enzymatic role that Kate mentioned, and the other is its interaction with another protein called CD31. And basically figure 4 just shows that CD31 is not part of this.
Yeah.
This figure 4 reeks of a reviewer that was obnoxious and was
Absolutely.
a CD31 biologist and was like, no, it's because it's interacting with CD31. And so they're like, all right, well, I guess we'll make a whole figure showing that it's not CD31.
Yeah.
Right. That was my interpretation as well.
Yeah.
So, but it's not CD31, so that's cool. It's the enzymatic part, but they don't really go into, as Kate mentioned, mutating the catalytic domain would have been real nice. I don't know if they know the catalytic domain. I know nothing about the biology of CD38 other than what I read in this paper. But figure 5 is where they get to the really interesting part of this.
Yeah.
And that is seeing if soluble CD38 could be used therapeutically. And the reason that this is important is that in people, a large problem with couples that are having trouble conceiving is that they're getting a lot of spontaneous abortion. So maybe fertilization is fine. And particularly if you do in vitro fertilization, where you take the man's sperm and the woman's eggs and you put them together in a petri dish and do fertilization in vitro, and then try to implant it into the mother. Often, if that doesn't work, it's often because you get the spontaneous abortion or you get a failure to implant.
Yeah.
And one of the reasons for this very well could be that you are not getting the immunosuppressive effect of the male semen. So what they tested then is to see if, at least in mice, if you could use soluble CD38 therapeutically to protect fetuses from this spontaneous abortion, which might be mediated by the mother's immune system. And basically they found that they could. Basically, in order to get spontaneous abortion, they would stress these females out after they were impregnated or after they were inseminated.
Yeah, they basically did what you don't want your animal technician to do, which is to go into the breeding colony and just like start clapping and yay, right? Because the mice, they freak out and they, the females get stressed and you do not get pups like that.
I just assumed that they played the scene from Dumb and Dumber where they are making the most annoying sound in the world. Just on repeat.
The technical scientific term for this is sonic stress.
Yes.
And so basically by stressing out these mothers after they had been inseminated, they had a much higher amount of resorption. It sort of recapitulated what we saw back in figure 1, in figure 2 with the CD38 knockout. So they have this higher level of reabsorption, so fewer pups being born. But what they found is if they injected CD38 into the uteri? I don't know what the plural is. Uterati. Yeah, that must be it.
That is definitely something I was thinking about. I was like, uteri? Uteruses?
In any case, if they give soluble CD38 therapeutically, they can get a reduction in the spontaneous abortion in response to sonic stress, which suggests that this might have a useful therapeutic benefit in people that are trying to conceive through in vitro fertilization, which I think is really cool. So a lot of times at the end of a paper, you want to sort of throw in your stock therapeutic benefit figure, and I feel like this actually delivers pretty well on that. This isn't sort of a hypothetical thing. It actually could have some real benefits for couples that are trying to conceive.
Yeah. No, I actually really liked the model at the end of all this. I know we beat down a little bit of the cellular immunology along the way here, but I actually really enjoyed this paper. And part of the reason...
Let's be honest, it was you.
Sometimes I beat down on the cellular immunology of some papers. That's maybe something I do. But no, I really did like this paper. I thought that the last figure, the sonic stress model, I thought was a really good application of these findings. So yeah, I liked it. And it's a big deal. Like this is actually something that costs a ton of money, and couples get stressed out over not being able to conceive. Like this is actually a big human health problem that not a lot of people talk about. So yeah, I was happy to see this.
Yeah, super cool. Is there anything else that we want to talk about with respect to this paper?
No, not really. I just think that figure 5A, it's kind of like the money shot, if you will. Oh, sorry. I had to do like one.
Thanks.
I had to do one dirty pun. I'm sorry.
Thanks, Kate. Well done. Well done.
But
maybe one thing that would be good to do.
It's very impressive.
Yeah.
The money shot.
The money shot. Very impressive. So that's the paper. Pretty cool. maybe some minor quibbles, but I think ultimately it's a very important story, and it, I think, illustrates something super interesting about the immune response and the immunity of pregnancy, which, as we mentioned at the top, is tough to study. And of course, this doesn't really address whether this is applicable in humans. As we said at the top, they did find soluble CD38 in human semen, but if it has the same mechanism, it's unknown. And there's still some open questions, but it's a really good preliminary finding, and I think could be expanded quite well. So before we head out, I just want to say, if you're coming to us from TWIV, welcome. Hope you enjoy it. And if you have questions or comments, please let us know. We don't get a ton of email, but we would be happy to read it on the air, a la TWIV, if we get some nice comments. So please do that. This has been Audiommunity episode 11. I'm Kevin Bonham with Kate Franz and Matt Woodruff. We are doing a revamping of the website. We've been having some problems with our WordPress-based site, and the feed got screwed up. So if that happened to you, I apologize. Should be all fixed by the time this podcast goes out. But you can subscribe from our website. There's an RSS feed, or through iTunes. If you just search for Audiommunity in iTunes, you should find us. And if you like the show, please leave us a rating on iTunes. It helps us move up in the iTunes listings. You can also leave feedback, as I mentioned, on the website, by commenting on this episode, or just send us an email through the website. There's a form there where you can submit a comment or a question. You can find links to some of the things we talked about and all of our previous episodes and minisodes, as well as some graphics, although we're a little bit delinquent on that. But you can find those at emmunity.org. That's EMMUNITY.org. And the music at the beginning and the end of the podcast was written and performed by Rachel Rennie. Woo-woo. We'll see you next time.
Peace.